We get going there. Right?
I guess let's get going. Okay, so it's our pleasure, my pleasure, to introduce the last seminar of this academic year in the Non-Commutative Geometry and Topology seminar. Our speaker from Swansea University in Wales is Tomasz Brzeziński, and he will speak towards non-commutative bundles with homogeneous fibres. Okay.
Thank you very much, Ray. Thank you very much, Karen, for invitation to give this talk in Prague. It's a pity I cannot be physically in Prague. I guess it's a beautiful sunny day there. Well, Swansea it's not looking bad today, so it's at least the advantage that I have is after giving this seminar, I can just go to the beach. Right. Okay, so this talk is based on the 3 papers that I have. It's a joint project with Wojtek Szymański from Odense. So I know there's one person in the audience, Sophie, knows him very well. I guess he's her supervisor. And the aim of the project is to, well, actually to try to understand what non-commutative bundles with homogeneous fibers might be. So I'm well, more algebraized these days than anyone else. So I will concentrate on the algebraic aspects. And as Ray said, Sophie gave a similar talk in autumn, so she probably mentioned more the topological aspects, the operator algebra aspects as well. So this will be a purely algebraic talk, and I realized that it will be quite technical. So when I look through the slides, revising the slides and preparing the slides after preparing the slides for the talk, I noticed that some stuff is quite technical. So I do apologize about the level of technicality. You might be lost in some who is playing in which position, let's put it that way, more football-like terms. Anyway, so as I mentioned, this is a joint project with Wojtek, and it's based on 3 papers. 2 of them already appeared. One was conference proceedings. One is a sort of special case. As the middle one, the quantum Flack manifold, the special case of what we developed further in the 3rd paper, which has already appeared. And I might use a bit of this paper later on if I'm asked about some details, and there is a demand to show any further details. Okay, so right, I already mentioned what the aim is, so but it never harms anyone if the aim is repeated, especially if the topic is quite technical. So we would like to understand really sphere bundles in non-commutative geometry, and to go beyond bundles with a circle as a fiber, non-commutative bundles of circle as a fiber, or S3 as a fiber, because in the S1 and S3 cases, these are both are quantum groups. They are Hopf algebras. The algebras of coordinate functions are Hopf algebras. So we end up with principal bundles, and this sort of bundles, from the algebraic point of view at least, it's quite well understood. So these are principal homogeneous extensions or principal homogeneous principal homogeneous principal comodule algebras or comodule extensions, so I will explain what the principal commodule extension is. Essentially, it's a Hopf-Galois extension, which is faithfully flat. Now, if we want to look at spheres, then we can interpret spheres as homogeneous spaces, quantum homogeneous spaces, quantum spheres, quantum homogeneous spaces. In classical geometry, as it's well known, you can see Sn as SON plus 1 by SON as a quotient space. The odd dimensional spheres can be seen as SUN plus 1 over SUN. So the upshot of this is that we would like to look at some framework, algebraic framework, in which we can study quantum homogeneous bundles with quantum homogeneous spaces. Right, so there are two motivating examples, and I will talk about those examples later on in more detail. So one example is the quantum flag manifold, SUQ3 divided by the action of the two torus. It was introduced by Stockman and Dijkhuizen, and we would like to understand it as a fibration with CP1Q as a fiber, so quantum or Podley sphere as a fiber, and over CP2Q, quantum projective plane. In fact, when we looked at this problem, we realized that with not much additional work, one can look at the the full variety of the full variety might be misunderstood in various ways, but the variety in the sense the many of the ways the quantum Podlej 2 sphere can be characterized with two parameters. That's what I mean, two-parameter version. And this leads to a two-parameter deformation of the quantum flag manifold. Again, the base manifold will be unchanged, so the quantum homogeneous, quantum projective plane. And another example is the twistor bundle. So this is a CP1, again, the fiber is CP1Q, so the Podlej sphere. Now the standard Podlej sphere. And the total space is the twistor, quantum twistor space, or CP3Q. And it turns out that as a base manifold, we get a quantum force sphere, but there are various quantum force spheres, and it turns out that this is a deformation defined by Bonecki, Ciccoli, and Tarlini. Okay, so these are the motivating examples that we wanted to study. And in fact, as you will see, the whole algebraic machinery that we built out of this example, well, it really stems from these examples. Right, so the main idea is that whenever we talk about bundles with homogeneous fibers, and since homogeneous spaces can be understood as quotient spaces, there is some group involved, and one can try to construct first a principal bundle, and then they quotient the fibers to get the homogeneous spaces as fibers. So bundles with homogeneous fibers somehow live in the shadow of principal bundles. So I better explain first what the non-commutative principal bundle is, or how we understood it in the algebraic terms. So as I say, it's purely algebraic interpretation, so it might be quite different from what Rita was talking about last week. So C is a coalgebra in this framework. So it's a minimal algebraic structure that we need to consider. we will think about C as encoding the quantum group which will form a fiber. P is an algebra. There should be an action of a group on the total space. So P represents functions on the total space, and the action of a group means the coaction of a coalgebra. C is just a coalgebra, so there is no multiplication on it. We can only demand that the P is a comodule. There is no compatibility between the algebra structure on P and the algebra structure on C, because there is no algebra structure on C. The next step is to define what the functions on the total space would be, and these are the coinvariants of the coaction. So they are defined in the way that does not distinguish any particular element in the coalgebra. So typically when we deal with Galois extensions, and quantum groups is encoded, or the coordinate functions of quantum groups are encoded in a Hopf algebra, we have a particular distinguished element, the identity, and we can use the identity to define the coinvariants. In the coalgebra, there are no such distinguished elements in principle. So we define those coinvariants in the way that this is this part of P over which the coaction is left linear. Okay, so B goes, so when here you see B row of P means that I act with element of B on the first leg of row of P. So it's an action, it's just multiplication in P. Okay, this immediately from this definition, it follows that B is a subalgebra. And again, from the definition, clearly the coaction row is left B linear. It's linear on the left-hand side B. We don't know what happens on the right-hand side, although there is some linearity, which I will mention. Okay, and then we say that the extension of coalgebras so is C Galois, or coalgebra Galois, if the canonical map, Galois canonical map. So again, it's the right-hand side here looks very much the same as that in the definition of B. So we use the multiplication in the first leg of the coaction is bijective. Okay, so that's a pretty standard by now definition, I hope.
So, Tomasz, can I just ask a historical question? Who was the first person to see this trick of defining, when you don't have a unit, of defining it in terms of bilinearity?
Okay, so probably the first person to see it was Takeuchi.
Okay.
So the story is that when we started studying those coalgebra bundles with Shan Majid, then we started with a distinguished element. And then we designed a particular structure to compensate for the lack of multiplication on C. And then at some point, Piotr Hayats visited Japan and visited Takeuchi, and Takeuchi mentioned that perhaps this can be defined without mentioning of the distinguished element. So I learned it from Piotr, and we tried then in our paper with Piotr about entwining structures associated with coalgebra Galois extensions. I learned it from Piotr, and Piotr just learned it from Takeuchi. So I think that's a fair history of the.
Thank you very much. Good to know.
Okay, so right. So now I will need a distinguished element, and that's what we normally do, that we have this distinguished element. So we will say that Galois extension is copointed if there exists an element in C such that row of 1 has this particularly simple form. Okay, 1 tensor E. What one can immediately find is from the co-associativity of row, E must be a group-like element. from the coaction property of rho. E must be a group-like element. Right, and then one can discover that actually the subalgebra of co-invariants is defined with the help of this element in the most natural way. Okay, so the example here given is the Hopf-Galois extension. C is a Hopf algebra, rho is an algebra map, algebra coaction, and the Galois map is bijective. Then E is equal to identity in the Hopf algebra. Now, to see that indeed this B here, as defined here, is the same as this maximal subalgebra over which the coaction is left linear, what one needs is the invertibility of the Galois map, or in other words, the existence of an entwining structure. So I think I will mention this entwining structure. Yeah, that's the entwining map happens next. Okay, so although C does not have an algebra structure a priori, the fact that the canonical map is bijective, even without assuming the copointed, making the copointed assumption, is that there is a particular map, psi, which is defined in the following way. So you take one tensor C, apply the inverse of the canonical map to it. So now we end up in P tensor over BP. And then we multiply with P from the right in P tensor over BP and apply canonical map. And this map has a very nice properties. It's in some way, it respects both the algebra structure of P and the coalgebra structure of C in the sort of obvious way. So you can think about the four conditions that you can write for the map psi to respect algebra structure of P and coalgebra structure of C. So for example, if you start with C tensor P, you can apply the coproduct to C, then you end up with C tensor P. Then you can shift P to the right by applying psi twice. But you can say, well, I could start with psi first, so swap C with P by using psi and then apply the coproduct. And the result is should be the same either way. And you know, this derivation of the counit, you can also write down what the axiom would be, and dually for the algebra structure of P. Now, this map psi really replaces the existence of the compatibility between multiplication on C and the multiplication on P, or the coaction and the multiplications. Well, there is no multiplication on C, but we have this replacement. So rho of the product of two elements in P can be expressed in this way. So we can calculate it on the rho on the product by using the map psi. So P0, P1 means that I applied rho to P, the Swidler notation. Okay, and then immediately one finds that rho of P is, in the copointed case, is psi of E tensor P. So there is you can recover the coaction just from psi. So in the copointed case, one could start with psi rather than with the coaction, and in a way that's what we done with Shan in this first paper in which we discussed coalgebra bundles. Okay, the next observation is that actually the canonical map, Galois map, is P bilinear. It's obviously left P linear. But you can define the right P module structure on P tensor C just in this way, using the mysterious map psi and wonderful map psi. And it's immediately, from the definition of psi, you can immediately find that that canonical map is actually the homomorphism of right P modules. Well, it's a usual trick that if we have a module structure on one module and a bijective map to another, or linear map to another, linear, the k-linear over the field map to the other module, we can transfer to a vector space, say, then we can transfer the module structure by using the isomorphism property. And that's exactly how you can think about it. Okay, in the Hopf-Galois case, the map psi is no longer that mysterious. It takes a very simple form. It's just we apply coaction to P, swap the order of C and the leg in the Hopf algebra C, and multiply. Okay. Right, so now there's a final definition leading to what a non-commutative principal bundle is in this algebraic setup. So an E-augmented principal algebra extension is an E-augmented C-Galois extension in which the canonical entwining map psi is bijective, and there exists a strong connection, which means that a left B module and right C comodule splitting of the multiplication map, so P tensor P to P is a multiplication map, well, there exists a left B module, right C comodule splitting. This is equivalent to say that P is phi flat as a left B module, but I don't want to define what phi flatness is, so it's much easier to tell that we have a map which splits the multiplication, which is both, the splitting is both B linear on the left and C collinear on the right. Now the assumption that psi is bijective in the Hopf-Galois case corresponds to the bijectivity of the antipode. And bijectivity of the antipode is something which safely in the geometric situations can be assumed. All quantum groups or groups obtained from the quantum groups in the sense of Voronovich or the Hopf algebras associated with quantum groups of this kind will have bijective antipode. So that's a very mild assumption, and I've written down what the formula for the inverse of psi is. Right, so just to summarize, we think about this psi as replacing an algebra structure on C, on the coalgebra, which is the fiber. And the bijectivity of psi just corresponds to the assumption, the bijectivity of the antipode. Okay, so the probably best known example is a circle bundle, also known as a strongly Z-graded algebra. Okay, so what we have here is an algebra which is Z-graded algebra. So we can split it into subspaces as a direct sum of subspaces labeled by integers, with the property that if we take an element from the part labeled by n and elements from the part labeled by m, we get an element in the part labeled by m plus n. Okay, but the strongness assumption is that actually if we multiply all such, every element, in other words, every element of in the part m plus n can be split as a sum of elements of the products of elements, one of m, the other from n. Okay, so we can always decompose the elements in fact in any degree. Okay, so so that's a strongly Z-graded algebra. We can take as just a coalgebra part of the algebra of functions on the unit circle, which is the same as taking the coalgebra of Laurent polynomials. So U and U inverse are all group-like elements. Well, I'm not really interested in the algebra structure here. So I'm just interested in the U and U inverse.
Hey, Tomasz, can I just ask a quick question?
Yeah.
In your definition of strongly segregated, do you require any compatibility between like Pn and P minus n? Like, is there a star involved here or something, anything like that?
No. So if you want to do a star algebra stuff and C-star algebra operator stuff, then you would require this. But in the purely, so I'm working purely algebraically. I will mention the star. I'm sorry about it. I will mention the star later on, I think, or maybe even not later on. I don't remember now. But no, in principle, we don't assume compatibility. But of course, if you want to have a full, well, I will mention star. Sorry, if you want to have a full extension to the topological situation, you would say that this U inverse is actually U star, and then the compatibility would be that Pm star is the same as Pm. Well, P minus M, sorry, I should say P minus M. Okay, so there's the compatibility. So in other words, when I write this coaction here, I would say that it's a star algebra map. Or star map. Doesn't have to be an algebra map. And it is in this case. You can introduce the obvious algebra structure of Laurent polynomials on CU inverse, and then it's an algebra map, star algebra map if U inverse is U star. Okay, so now I will increase the level of complexity if it's not what I said so far wasn't complex enough. So for the rest of the talk, we should keep in mind the simple stuff, that whenever B, P, and C appear, then we have a principal C comodule extension. So this is somewhere in the schedule in the background of what I'm doing. So now, but I want really to have quantum homogeneous fibers. So for this, I need some subgroup of a group, which means that I need to have a surjective coalgebra map, or actually, I'm not even assuming it's surjective for this generality. We just have two coalgebras. I have this principal comodule extension in the background, and now I take another coalgebra and the coalgebra homomorphism from C to D. And the fixed points, so this induces, as I will explain in a second, this will induce, this induces a coaction of D on C. I can take the fixed points of this coaction defined in an appropriate way. And this will be this will represent a homogeneous space. Although in this generality, again, this homogeneous space, so the algebra of functions on the homogeneous space will not be an algebra. So it's a bit, I don't know how to tell it, but maybe it's not very honest what I'm saying. So it's not really an algebra of functions in a quantum homogeneous space. Okay, so remember, we have this co-pointed situation. So we have this group-like elements E. Okay, so I can, since pi is a coalgebra map, I can project it down or pass it down to D. I will call it E bar. And since I have this E bar, I can define some sort of fixed points with respect to this E bar. Okay, so starting with the induced D coaction, okay, so I can induce rho is a coaction of C on P. I can send it down to D. I will have a coaction of D on P. And then I will set A to be the fixed points, but this is not necessarily an algebra. Okay, so these are just vector subspace of fixed points, fixed by fixing this E bar. Okay. But what we can already learned is that A is a left B submodule of P. So it is not a subalgebra of P, but it's since the coaction rho was left B linear, we can easily check that, that A is a left B submodule of P. And this will play the role, as I say here, the total space of the bundle with the homogeneous fiber. So let me stress again, on this slide, A is not necessarily an algebra. Now, the homogeneous fiber, quantum fiber, is defined just as I mentioned. So I can produce the coaction of D on C by sending the co-multiplication, this delta here is the co-multiplication on C down to co-multiplication, well, to D on the right leg. And then I can take the fixed points. Again, this with respect to pi of E. So this pi of E is the same as E bar. Okay, again, X is not an algebra because C is not an algebra. So one can't expect to be a subalgebra, but it is a left C coideal. So if I apply co-multiplication of C on X, I will end up in C tensor X. So in other words, X is a left C comodule. And because we have this left C comodule property on X, I can consider cotensor product. So P has a right C coaction, X has a right C coaction. So I can define this cotensor product, all elements which are equalized by the C coaction on P and the right and the C coaction on X. And further, I can consider the second cotensor product when since I have a left C coaction on X, I can send it down on the leg of C to D. So I will have a left D coaction on X. And that's what the second subspace of P tensor X is. Okay, so that's it is quite clear that generally the B coaction will restrict to P tensor X. So B action will restrict to B tensor X because both rho and rho bar are left B module maps. And if perhaps I should say that if pi is surjective, then I think if pi is surjective, then we have this inequality because C is somehow bigger, so we cut out the bigger to equalize the things. We have to remove a chunk of the bigger chunk of P tensor X. Okay, so I need to sip some water. Right, so just to summarize the setup. So we have a coalgebra with a distinguished group-like element. P is a principal C extension over B. Now I have this space of coinvariants under the D coaction, or perhaps I should say the next step was to introduce this pi, which sends E to E bar. So I have a coalgebra with a distinguished group-like element. And then I can look at the coinvariants, or E bar coinvariants under the induced D coaction, and X will play which sits inside C, will play the role of the fiber. A will play the role of the total space. So there's the coaction, the invariant of D coactions on P, and finally the base will not change. Okay, so that's the general setup, and now the questions are what we can actually say about this situation and you know, why is it useful? This will be the next thing to say. So the first theorem is that actually A is isomorphic to this cotensor product. So why is this important? And that's left B modules. Why is this important? Well, because now we can see that somehow X sits inside A. So X is supposed to be a fiber. So this first point somehow tells us that A is fibered by X.
Sorry, Tomasz, I just have to ask a question. My power went out for a second. But what is A again? The definition of A.
Okay, so A is defined as the coinvariance of the induced coaction. So P coacts on C coacts on P. I have a coalgebra map from C to D.
Mm-hmm.
And so I can induce the coaction. So let me go back to the definition. This is just the elements.
Okay, so it's the D invariance with respect.
Yeah, D invariance. Yeah.
Sure. Thanks.
With respect to this group-like element E bar.
Mm-hmm.
Okay, so this is not an algebra.
Yeah, thank you.
It's just left B module. That's what we know. And what we know now is that actually it is fibered by X in some sense. Okay, because as a left B module, it's isomorphic to P, this total space of our bundle in the shadow, and cotensor product with X. The next thing is that it's actually a bundle in the sense that it's a projective B module. And the last thing is that the canonical map, well, is bijective when restricted to P tensor over BA. So remember, A is a left B module. The coaction when restricted to A, well, this can be, canonical map can be written down, so it can be restricted to this one. It can be restricted to this the left-hand side, and we'll end up exactly in P tensor X. Okay, so which tells us that unless P is equal to B, we are not dealing with a principal bundle. Okay, we have some isomorphism of the property of the canonical map restricted to, so if I restrict it to A on the left, the image will end up in X on the right. Okay, so the next diagram just indicates that I filled in just this bit. I have another interpretation of coinvariance, which connect the coinvariance with the fiber X. But so let me stress it again. A is not an algebra, X is not an algebra.
Is A finitely generated or not necessarily?
No, it's just projective.
Okay.
It's just projective. P is a projective as a left module. It's equivalently projective because there's this splitting of the multiplication map, which is left B module splitting, which tells us it's projective, but it's also compatible with C coaction. So there is a bit more than projectivity. So in this case, we have a projective module, but not finitely generated. Just like the principal bundle is not finitely generated, it's just projective as a module, the module of sections. Okay, so the second main theorem, and in fact it's a main theorem, unfortunately requires a bit more assumptions. So you have to brace for some bit more of notation and structure that enters, because as you can see from this, in some way, I would say that's a minimal what one can have at the beginning. That's we definitely have to have C and D to produce this homogeneous sort of quantum homogeneous space. But then there is very little control of everything. So there is this environment of principal bundle. So P, C, E, rho, this is a principal comodule extension, this is still there, but now I require a bit more. So I assume that there is a Hopf algebra with a bijective antipode.
Sorry, Tomasz, can I stop you once just to go back to get all of this clear in my head?
Yeah.
How is, so P is the, sorry. No,
This
okay.
slide or the next one?
It's okay, thanks.
Okay, so now I introduce some more complete symmetry in the picture. This symmetry is encoded in a Hopf algebra with bijective antipode, the quantum group. So P is a right H comodule algebra. Okay, so that's a compatibility of multiplications as well, with a coaction which I denote by delta. C is a right H comodule, H module coalgebra. So C is not an algebra, but we can, maybe I will close the window because there's some noise. But it's a coalgebra, so, and H has a coalgebra structure, so I can require, well, has a coalgebra structure and an algebra structure. So in a way, C is a dual to A, right? So we have an action of H, which is compatible with the comultiplication in this way. D is a right H module, and pi is H linear. Okay, so I have this Hopf algebra which somehow acts on everything or coacts on whatever is in the picture. And canonical map is right P linear with respect to the P action on P tensor C. They say, yes, in this way. And if these conditions are satisfied, if these conditions are satisfied, so this P action, the right P action of P on tensor C is provided by the entwining. So if these conditions are satisfied, these are not necessary conditions. I don't think it's necessary, but it's are sufficient for A to be an algebra. And then I can show that actually A tensor over BA is isomorphic with P cotensor product over D with X by the canonical map. So when I restrict canonical map to the subalgebra, now A is a subalgebra of P, to the subalgebra, then we have this isomorphism, which is like a canonical Galois property, but note that on the right-hand side, there is a slight twist because we have this P, not A. Okay, so that's in a way the main theorem. I will summarize it in under these assumptions. In the next slide, we'll just show the diagram, and then I will just mention the examples. Okay, so our standing assumptions, we have a principal C extension, right? P is a principal C extension of B. We have this Hopf algebra, which acts on C in the way compatible with the structure of C, acts on P, sorry, coacts on P with the coaction compatible with the algebra structure of P, and acts on D. And pi is compatible with the actions. Okay, then in this case, I can identify A with as before, so the conditions of the previous theorem are satisfied. A is an algebra, although X does not have to be an algebra. So X still does not have to be an algebra, but A is, and we have this isomorphism. So before I move to the next slide, when should I stop?
Usually, I mean, we have, I guess the Prague standard is an upper bound of an hour and a half. But so you have some time after the hour.
Okay. So I will continue and just give you the examples. And
Yes,
so
please.
I know it's a very technical stuff, so it's not easy to when I don't. How can I put it? Well, in the past, I did some work with weak Hopf algebras. And the weak Hopf algebras are wonderful things to work with, but I have some mental problem with them. Namely, if I stop working with them for a week or two, I have to learn them from scratch again, because I forget all the tricks that one can do. And this is a similar situation that, if I don't look at all those structures around, I will just, for a week or so, I will forget what is needed for what. So so I appreciate it's a very, it's not an easy thing to grasp. So let's just move to.
Thomas, can I ask you a question?
Yes,
concerning the diagram of the previous. So can you say something like you are in the category of representation and co-representation of H?
Yes.
And you are studying some specific constructions there. Maybe you can make this vague statement I made more specific. Would this help framing your construction?
Yes. So what you can say. So we know that since H is a Hopf algebra, the category of both the category, well, there are two different categories. I don't really know how to phrase it categorically, but the category of comodules of H is monoidal, and the category of modules of H is monoidal. So, so I'm saying, in other words, that C is a coalgebra in the category of H modules, left H modules. Was it left or right? I'm already right H modules. And P is an algebra in the category of right H comodules. But then D is not in the category. Maybe it is. Maybe it will also have this compatibility condition. So I mean, frankly speaking, I tried to interpret this in this categorical language, but because I'm dealing with, in a way, two different monoidal categories of modules and comodules, I wasn't able to. Maybe one should take some product category. I don't know.
I see.
Okay, so before the example, so there was a lot of complicated conditions, but it boils down to something not that complicated. So this condition D, that CAN is a right linear map with respect to the canonical Galois map of Galois map, with respect to the P action induced by psi, tells us simply, it actually gives us what psi is. So this means that the psi is actually of the so-called Doi-Kopinen type. So whenever we have an algebra and a module coalgebra of a Hopf algebra, we can define this map where Pi tensor Hi is the H coaction on P. Okay, so I didn't use the Swidler notation here because I used it for the C coaction on P. There are too many coactions here. So that's an H coaction on P. And this will satisfy all those nice conditions, compatibility with multiplication and commultiplication for psi. And its inverse has, again, very simple form. We just use exactly the inverse of the antipode for the Hopf algebra.
Sorry, Tomasz, can you remind me what psi is again?
So psi is the entwining map, which the exact definition is given here. So we take one, so it swaps C tensor P with P tensor C. We take C tensor P. So first we apply the inverse of the canonical map to 1 tensor C. We multiply on the right with P and then apply canonical map. Okay. So it's a transfers a module, P module is a transfer of a P module structure from P tensor B over BP to P tensor C.
Okay, thank you.
Okay, so in this case, when in this situation, I can actually write down what psi is, and that's why it's assumptions were actually needed. Okay, so the examples. The first example, the quantum flag manifold. Right, so we start with, in this case, H is equal to C. We have S and H equal to C is the coordinate algebra of the quantum group UQ2. Okay, so this can be thought of as generated by this matrix. It's a matrix of quantum groups generated by this matrix, where, so now there is a star. So U is a central unitary element, generator, and alpha, gamma satisfy the usual Voronovich conditions for SUQ2. Okay, so alpha gamma is Q gamma alpha, and so on and so forth.
So U is just the inverse of the determinant, is it?
Sorry, U
is determinant or inverse determinant, basically? No.
No.
So I mean, formally, you can define U2 as taking SU2 and adding a formal inverse to the determinant.
Yes, but or you can define it as SU2 tensor U1 and twist it appropriately. So that's a.
Okay. Yeah. That's fine.
Yeah. So this U1 part is U. So can I think about it as a determinant? Well, yes, it's an inverse. Okay, so you are right. This is an inverse of the determinant of this matrix.
Yeah, that's yeah, exactly.
Yeah.
Great. Thanks.
Or the quantum determinant. Okay, so now if I look at this particular subspace, it actually turns out to be a star subalgebra. S is a parameter from 0 to 1. Q is a real number between 0 and 1, as always in this game. And we can check, it's not an easy, not a straightforward check, but you get a Podley sphere out of this. So psi and zeta generate a Podley sphere, and these are the relations it satisfies. So it's actually these elements generate there's 3 elements. So zeta, psi, and zeta star generate subalgebra, which is isomorphic to coordinates of the coordinate subalgebra algebra of coordinate algebra of the Podley sphere. Q equal to S equal to 0 is the standard one. Right. So S somehow measures what is it? Latitude, right? Going from the equator to the pole. Okay. Now I can look at this ideal. It's a right ideal. Sorry, I'm looking at the right ideal generated by psi, zeta minus S, zeta star minus S. It's not a very mysterious ideal, ideal. It's a right ideal at the moment. That's how it is defined as a right ideal. because what I have here is that if I restrict the co-unit in my OUQ2 into this subalgebra, then these are just these things will they vanish? No, they don't vanish, but that's right. Anyway, okay, so J is a co-ideal and the right ideal. So that is a right ideal. So we repeat it too many times. It's obvious because that's how it is defined, but it's also a co-ideal. D, when I take the quotient, so since J is a co-ideal, D will be a co-algebra. I take the quotient, but it also is a right ideal, so it will be the result will be OUQ2 module, right? OUQ2 module. And pi is a coalgebra epimorphism, but it's not an algebra map if S is not equal to 0. And in fact, what Müller and Schneider proven in the 90s, mid-90s, or late 90s, or early 2000s, was that early 2000s, that in such a situation, a coalgebra obtained in that way, this D, first of all, is generated by group-like elements, and secondly, that X, that this the coalgebra co-invariance is actually equal to OSU2QS.
But then, Tomasz, this should follow basically what you're doing is just Takeuchi's equivalent. So from faithful flatness, this will follow from a result of Takeuchi's paper.
Yeah.
20 years earlier,
yeah. I mean, that X is equal OS to QS, the co-invariants are equal to this subalgebra. Yes, that's a Takeuchi faithful flatness. Okay, so I've, for your information, I've written down what's the group-like spanning element of DR. Since we are dealing here with the products of non-commuting monomials or the non-commuting expressions, one has to specify from which side we are multiplying, from the left to the right or right from the left, but I don't remember. But from one, it's actually, it says, well, so I knew I wouldn't remember, so I wrote it down. We multiply from the left to right. Okay. And so we can think about it as, I mean, it's a very arbitrary, in a way, it's a very arbitrary interpretation that this is a coalgebra of, the coalgebra of functions on two torus. Okay, because it's we have two generators, U and V, and all the negative powers of both and positive powers of both. So you can think about them as, but from the coalgebra point of view, this is just isomorphic as any coalgebra with countable many group-like, spanned by countable many group-like elements. So from the coalgebra point of view, there is no distinction, but we can think this as a heuristic way of thinking about it. It's actually we are dealing with a two torus. We get some sort of two torus. Okay, so the second example is this is the same quantum flag manifold. I'm just getting to the flag manifold. Right, so now P is SUQ3. Okay, so far I described H, I described X. I haven't yet said what A is and what P is. So for P, we take SUQ3. So this is a standard Voronowicz matrix quantum group. So it's generated by the matrix, 3x3 matrix, and some relations, or the standard stuff. And OSUQ3 is a right UQ2 comodule algebra in a very simple way. So UIK, UIJ, UIK are those, it's a full matrix of 9 entries. And now I'm projecting some of those entries to 0, the top diagonal one to U, and the remaining, the lower 2x2 matrix to those generators of SU2, generally multiplied by the inverse of the determinant. Okay, so so it's easy to see that it's a comodule. That's a comodule because we are dealing with matrix algebras in both cases. So that is definitely a comodule map. I mean, that defines a comodule structure. That it is an algebra map as well. It requires some calculation. Okay, so the next observation is that actually this is a comodule, principal comodule algebra with the coinvariants, which are the quantum projective plane of Waxman-Seubermann. Okay. Right, and the last step is to calculate. So now I know what the base will be. I know what is the total space for the underlying principal bundle. So now I need to carve out the fixed points, and from calculation they just come out, and they are defined in that way as SUQ3 divided by this correction of D, the coinvariance under correction of D. But I think about D as two torus, so we end up with flag manifold, and this is a sort of generalization of the Stockman-Dayhuizen flag manifold, because in their case they had the second parameter was 0, so it corresponded to the standard Podley sphere, but here we have a second parameter. Okay, so I think the next slide will be the diagram, which tries to summarize everything what I said. Okay, so in this particular situation, H is equal to C. So obviously C is, but H is its own comodule algebra. It's no problem. We have a H linear coalgebra map. So again, this property that's H acts on D is satisfied. And now the fiber is CP, that's a quantum Podley sphere. Right, and coinvariants, well, they all fit the second assumption of the second theorem, so we end up with an algebra. It's an algebra of coordinate algebra of the flag manifold, quantum flag manifold. Okay, so that's how this example fits in the framework. So let me just say a couple of sentences with show you the diagram, the last slide of the other example, the twistor bundle. Okay, so that's an example in which there is a separation between H and C. Okay, so what happens here? So H is UQ4. So now these are 4x4 matrices in which we can embed quantum 7 sphere just by, in our conventions, by taking the 4th row of this matrix. Then we have so this bit here, it's actually embedding P into, so S7Q, excuse me, into UQ4. it's a part of the work of Bonecchi, Ciccoli, Tarlini. This map R is there's a particularly designed H linear projection down to SUQ2. And the fixed points are the version of a quantum sphere. So that's a work of Bonecchi, Ciccoli, Tarlini. And then together with Dąbrowski, they shown that that's actually it's a principal extension. So seventh sphere is a principal, quantum seventh sphere is a principal SUQ2 algebra extension, a principal algebra, the principal algebra extension over this fourth sphere. And again, everything fits into the framework. So we have a Hopf algebra map to functions on U1. And then if we look at this, those coinvariants under this coaction, then actually what we can recover are three-dimensional quantum projective space. Again, it's a Waxman-Soibelman type. And okay, so we can interpret it as a non-commutative bundle with the fiber CP1Q, which is obtained. So if you divide, so that's this part here. If you think about this bit here, okay, that's just a Hopf fibration, quantum Hopf fibration. Three sphere, two sphere, and over a circle, or the fibered by circle. Okay, so I think I better stop. I've already overrun the time allocated, so sorry about that. A lot of problems. I mean, it's a complicated picture, I understand, and I understand that Sophie is working on the topological aspects of this kind of construction, C-star algebra framework, operator algebra framework for this. One thing that is completely missing from this is a differential aspect of all this. But there was a plan a couple of years ago, perhaps, in which Karen and Re and Wojtek were involved, that we all meet in Edinburgh, somewhere nice in Scotland. But some nasty virus put a stop to that for a time being. So, okay, thank you very much.
Okay, so are there any questions from the audience?
Hello, I have a very naive question. In the case when C is a Hopf algebra or some probably quasi-triangular structure, will be your map psi, as I remember, will be kind of some braiding type thing?
Well, it's not a braiding. It's not a well. No, so the answer is no. I mean, braiding could be an example.
Mm-hmm.
We think if it's not a
because what inspired me for these questions, I think formulas on the page number 16 before.
Okay.
Yeah, it looks a bit like braiding coming from Jeter-Drinfeld structure, right?
No, it's a different kind.
Okay.
From the Jeter-Drinfeld structure, you would have a joint sort of coaxial or action.
Mm-hmm.
So it's a different. Jeter-Drinfeld braiding is different because you don't have the coaction, which would the action, the way it acts. It's not a comodule algebra action. Module algebra action. So there you can define psi associated with, so satisfying those properties with the Jeter-Drinfeld. And that's what you would get in the braided situation with the quasi-triangular case. But not this one. I don't think this one.
Okay, thank you.
I think Rita has a question.
Yes, I have a question. So if you go back to the bigger picture, the one that you put before. That's the one, right?
Mm-hmm.
So I was reading with interest the work of Ayats about reduction, quantum symplectic reduction.
Mm-hmm.
And I was wondering, because it looks kind of dual of this picture. Instead of having a B inside A inside P, you get somehow, surjective maps there. I was wondering if you can see some relation between what Ayats does and what you're doing here, kind of dually or not, or if it's totally different.
Tomasz seems to have disappeared.
Yeah, I don't. So my question was too much.
I think the question was too difficult. It's exactly what happened.
All right. Okay.
Well,
I will. It's okay. I don't.
No, I mean, I think his connection is broken, so he's probably trying to get back. But,
Maybe someone should send him an email in case he doesn't realize he froze.
yeah, I can do that right now.
Or he just really wanted to escape the question.
Maybe he really wants to escape the question.
Possibly it's just a question. I mean, there is nothing to do with it, possibly.
Ray.
Yep.
Alessandro was saying these reminded him of your principal pairs.
Yes, this is what I was thinking as well.
Yes.
Oh, that's all right. See someone's head.
Okay, I sent him an email.
I can ask him through mail this question, and
yeah,
I mean,
let's give him a minute, and if then, I guess maybe I don't know.
So do you know how they relate to your principal pairs? Is it obvious or?
Not completely clearly, but it reminds me. It definitely does. Yeah. I did not see this the first time around, but the second time it's.
But Ramon, you don't have a surjective map for. You remember you were telling me this. You don't have in the examples you do, but in your definition you don't, right?
Yeah, well, I guess in the specific one that we're looking at now, the one that I was talking to you about earlier, then it exists.
I see.
So yeah, not in general, but for the specific examples, yes.
Okay.
I mean, of course, this generalizes because he's looking at coalgebras and not Hopf.
Yes. Not only this, but in your case, the complex structure is strictly related to that. And in this case, he already has the complex structure somehow, right? So it's not, I think if they appear, they don't look the same to me. Philosophically, they're not, I think, but.
Maybe. I also, I mean, one of my questions was going to be quite restricted to, and sorry, I guess, of course, it's so, this picture is there.
I'm sorry, I lost, probably I said something wrong. I don't know whether Piotr was listening and just switched off my Wi-Fi connection. So, okay, so I will try to reconnect with the screen.
So did you hear Rita's question or did she need to ask it again?
Well, yeah, I heard Rita's question and I even started answering it, but I think it was lost.
You didn't hear any part of your answer, so.
Okay.
Sorry? Hello?
Yep.
Yeah, I'm there. Okay, so as far as I remember this Piotr's reduction process, it was about reducing principal
Can't be a coincidence that Piotr.
bundle to a
bundles.
principal bundle by reducing the fibers. So
Yes.
so in that sense, it is similar, yes. But it goes
Seems to
a
me
bit,
the dual picture.
well, I'm not even sure if it's a dual. And the point here is that we don't have the fiber is no longer a coalgebra. Well, the fiber is no longer a coalgebra or a algebra.
I see. Okay, that is important. Yes.
That's important. So that's why we don't get this
Okay.
Galois map. Although there is some isomorphism, just like.
Mhm. Okay, I see the
Here,
point.
But
Thank you.
it's not a principal.
No, it is different then. No, you're right.
It is
Sorry
different.
for the
It is
question.
different. Yeah.
Okay.
Okay, so in that case, I have a few questions to ask as well. So the first is, could you go to the diagram where you took the specific examples?
Okay. The first one or the second one? Where exactly there are
That guy, yeah, I guess the last slide. So the U2, well, the OQ-U2 coaction, this should really be on the left. No, I'm sort of confused about your right and left coactions. This final H symmetry that you have.
everything is from the right.
Everything is okay. This
Everything is from the right, and that's why in the next slide, okay, we had to take the row in this matrix as a seventh sphere rather than a column. So there are two conventions. You can take the column or the row as generating the subalgebra of the sphere, and this would move you from the left to the right. And now everything here is on. All the coactions are on the right, or the actions of H are on the right. B is so what is the only action on the left is that of B, of the fixed subalgebra. So the modules are P is the left B module.
But then if you look at, let's say, look at your description of CP3 as the cotensor product, OQS7 is going to have, well, I guess, yeah, you're defining OQS7 with respect to a coaction on the right. So that means that you have a coaction on OQS7. I mean, if you're understanding it as inside in UQ4, there should be a coaction on the left with OQ of U4. Maybe I'm just misunderstanding something. Maybe it's too technical a question.
So it is a, yeah, it is a, okay, so UQ4, I see what you mean. No, so UQ4 acts on P on the right. So we have so
okay.
So it's a left version of the, so it's a left version of a, so this part proven by Bonecki, Ciccoli, Dąbrowski, Tallini, it's a left version of a Hopf-Galois extension.
Okay.
Okay, not the right coaction, but the left coaction, which in fact is equivalent because of the bijectivity of the antipode. You can move from the left to the right quite.
Okay, so you basically just, I can think about it as well. Yeah, it would be on the right. Okay. My next, this is maybe more a comment.
So let me have a look just to make sure. So that's a paper. It's all those quantum twister bundle that is. Okay, I don't know if it makes sense to go over it. Okay, so that's a definition of the seventh sphere. Okay, never mind. But the H in all this picture, H acts on P from the right and acts on C and D from the right as well.
Okay. And my next question then, it should be, I guess, that this generalizes to higher full flags and higher twistor bundles. I mean, there's no reason why it shouldn't.
Say it again.
It should extend your whole formalism up to higher rank flag manifolds and twistor bundles.
That's the hope, yes. If it fits into the into this general picture, but what we found was it was quite well. There are quite a lot of technical calculations that had to be done, and that's what we were hoping to get when we got together in Edinburgh, some more conceptual point of view on all this, so that we don't have to go through those calculations and use some more conceptual arguments, that actually what we calculate will be what we want to get, right? That's just like the Takeuchi or Miller-Schneider observations, but you don't need to calculate that this algebra D in this particular case is generated by or spanned by the group-like elements. You know it will be spanned from the group-like elements, and you can use it to find out what they are. And it's just like in this slide, it's not that easy to guess what they are. But you know that this is a coalgebra which is spanned by group-like elements.
And then I would say for the differential calculus, though, Peter was in the audience and myself, we found for all the A series full flag manifolds, of which your guy is the lowest, an example, found a differential calculus coming from this PPW theory. So they had made a canonical differential calculus that has classical dimension. It has a complex and Kähler structure. It restricts to, let's say, the Heckenberger-Kolb calculi and the Grassmannians in particular on projective space. So it should be possible to fit that in and try to get a non-universal, a quantum principal bundle, a differential quantum principal bundle picture on these examples. I would guess it works.
It should, yeah. That's what I would hope for. But again, there's something that can be done in those particular examples, where the fiber actually, so in all those examples, well, all two examples that we have, both A, well, that's what was part of the theorem, is an algebra, but also X is an algebra. Which even in the second theorem, where we have that A is an algebra, we don't know whether X is an algebra. So how do you talk about the differential structure on something that is not an algebra? It's not that
no, it's not that
easy. But in those examples, yes. So that so you have those differential structures, and some of them definitely fit in the picture, should fit in some way. And none of this map R here is not an algebra map. That's one of the points of the Bonecki, Ciccoli, Dąbrowski, Tarlini construction, that you don't get a Hopf-Galois extension. You actually get a coalgebra Galois extension, because your coaction is not an algebra map. So again, this creates some problems of compatibility between the differential algebra structure and the rest. So that, yeah.
So are there any more questions from the audience? No. In that case, I'll finish with one comment very quickly. I think the projective spaces were actually introduced by Meyer, a student of Shan first, and then reappeared in Waxman and Seibelman.
That's okay. So I won't comment on that.
Okay.
I'm simply not sure.
Okay.
So what I can tell you is that I was sitting with Ulrich in the same office in Cambridge.
Okay.
I was a student there. He was a student. He was a bit younger, and but I'm not sure what is the. I mean, I think that Ulrich was showing the principal bundle structure on them.
I know he defined. I know it because I used it in my thesis. Quantum projective spaces, quantum homogeneous space, in the 94 or something. So it should be. But anyway,
around that time, yes, yeah. And the Waxman-Seibelman
was 2000 or something.
No, it was earlier.
It was earlier.
I think it was earlier. Let's have a look at the references. 91.
Oh, okay. Okay, sorry. So then you're completely correct. I'm wrong.
So that's algebra functions of the quantum SUM+1 and odd dimensional quantum spheres, and then the projective space appears there.
Okay, I didn't know that. Okay, thank you. Okay, so in that case, since there are probably no more questions, thank Tomasz again for a very interesting talk.
Thank you very much for your patience, and have a nice summer.
Yeah, same to you.
Okay.
Thank you.
Attenzione, abitano.
I'll be alone each and every night. While you're away, don't forget to write. See you in September. See you when the summer's through.
So I think this is the last one.
Yeah, that's it. We're done for now.
Okay, when you guys resume.
Yeah, I don't think we know yet, but we will definitely let everyone know when we.
Okay.
All right. Bye.